So in this final video, we're going to take a look at being able to sketch some quadratic surfaces given the equations, and then to be able to describe the key characteristics of that equation. Right, so our first example we're taking a look at should be a fairly easy one to try to work with. So we have this x minus y squared minus z squared over 4 minus 1 is equal to -1. One of the things we can do right away is identify that it's going to be on a page 2 potentially, and that's just because of this x is linear. Right? So I'm going to add everything to one side except for that linear term, and we can rewrite that as x equals y squared plus z squared over 4. We know that this is going to be one of those type 2 or page 2, so we have a linear term. So we have one linear term. They're all positive, and the linear term is the x variable. So let's see what that means if we were to go back up, and we're going to look at page 2, and it looks like that our friend the elliptic paraboloid is going to be the quadratic surface that identifies best with that equation. So we have a single value, which is going to be x, or a single variable. We have all positives, and since x is the one that's the linear term, then it's just going to expand upon the x-axis. Right? So a rough sketch of this, if I can do my best with this, might look something like this. Right? And this is our x positive, z positive, y positive. Right? If I were to describe this, okay, we would say that it's certainly an elliptic paraboloid. The vertex is at the origin. And another thing that we could say is that expands on the z-axis. Or I'm sorry, on the x-axis. Alright, so that would probably be the best description that we can give of this. Of course, we can always go to the GeoGebra app and verify this by graphing it. A second example, not as easy. We have this x squared plus y squared plus z squared, but now we have this linear term. So now we have both a quadratic and a linear term. All right. This is a problem that we saw a little bit earlier in the course. In fact, it was on the very first guided notes, where we might have to use an algebraic technique to write it into a form that we like. So let's rewrite this by grouping the y's. And you'll probably remember that technique that we used is completing the square. All right. And remember, what you do is you take half of the middle coefficient, divide it by 2, or I'm sorry, you take half the middle coefficient and then you square it. So that's going to be -2 over 2 is -1, -1 squared is +1. So we're going to add 1 to both sides. And so we end up with x squared. Remember, we can now factor this because it's a perfect square trinomial. Take the square root of the first, square root of the third term, and then just drop the sign in the middle down. So that becomes y minus 1 squared, and then finally z squared is equal to 1. All right, so let's understand what this means in the context of the quadratic surfaces. All positive. All right, so all of our coefficients are positive. All quadratic equal 1. Right? So it's definitely going to be on page 1. And if we go all the way back up, on page 1, we notice that this ellipsoid, where they're all positive, is going to be equal to 1. And the other thing that we notice is that all the coefficients of the quadratics A, B, and C are all 1. In other words, x, y, and z are all going to be 1. So in fact, we actually have an ellipsoid that's a sphere. Right? So let's go back down and classify this. So if I was to graph this, all right, or even explain it, let's explain it first. So it's an ellipsoid. Okay. In fact, it's a sphere where A equals B equals C equals 1. Okay. The center is at the point 0, 1, 0. Right? And remember, we go back to the very definition of what a sphere is. And we know that the radius is the square root of 1, which is 1. Right? If I was to graph that, essentially we have the unit sphere that's centered at 0, 1, 0. Right? So I'd probably get something like this if I were to graph as best I can. Right? One final example. So we have 9x squared plus y squared minus 9z squared. So we have a much more complex equation to deal with. Right? So a couple things we're going to do. We're going to group the x's, y's, and z's together. We're going to subtract 4 from both sides. We can't divide by 9 as we did earlier in the course because we don't have the same exact variable, or we don't have the same exact coefficient. Right? So we're kind of stuck at this point. So I'm going to group this as 9x squared minus 54x plus y squared minus 4y minus 9z minus 54z equals negative 4. Now, anything with a coefficient that's not 1 in front of the quadratic, I'm going to factor that from that set. All right, so I'm going to rewrite this as 9x squared minus 6x. I'm going to leave a space. The second one, y squared minus 4y, leave a space. And we're going to factor out a negative 9. And we're going to be left with z squared plus 6z. And we're going to leave a space. And that's going to be equal to negative 4, excuse me. All right, so now here's the trick with this one. We have to be really careful when we complete the square, and even more careful when we add constants to the right-hand side to balance the equation. Right? So let's check this out. We're going to take half of negative 6, which is going to be negative 3. Negative 3 squared is going to be a positive 9. However, we are not going to add just 9 to the right-hand side. That's incorrect. What we are going to do is we're going to multiply 9 times 9, and that's what we're going to add to the right-hand side. So we can't forget that we're actually adding 81 on the left-hand side, so to balance on the right-hand side, we also have to add 81. Half of negative 4 is 2, negative 2. Negative 2 squared is 4. So we're going to add 4 to the right-hand side. And then finally, very similar to the previous, half of 6 is 3. 3 squared is 9. All right? So we're going to multiply, and we're going to add 9 times negative 9 to the right-hand side. Okay, and again, because that has a coefficient other than 1, we have to multiply by that coefficient whenever we add. All right? Now we can simplify the expression and factor it down, and let's see what we end up with. All right? So if I simplify this, I have 9 x minus 3 squared plus y minus 2 squared minus 9 times z plus 3 squared. And the good news is for us, it's easy to compute because the 4 and the negative 4 go away, the negative and the positive 81s go away, so we're left with 0. So now what do we have? Well, we have all quadratic, we have it equal to 0, and we have one negative. All right, so since it's equal to 0, we know right away that we're going to be on page 2. All right, so let's go all the way back up. And fortunately, we're almost done with this. So we're on page 2. We have all quadratic, we have one negative, and that means we're dealing with an elliptic cone. And again, the cone corresponds to the variable whose coefficient is negative, would be the axis of expansion. So in this case, when we go back down here, this is going to expand upon the z-axis, since the coefficient of z is negative. All right, so here's how we describe this. This is a cone. Okay. The vertex of the cone is going to be at 3, 2, -3. Okay. And then it's going to expand on the z-axis, or it's going to expand parallel to our z-axis. It's not going to expand on the z-axis, but it'll expand parallel to that. All right, the axis of symmetry is actually going to be z equals -3. All right, if I was to plot this as best as possible, it's not going to be a good plot, but I'm going to try it anyway. Just to give us a little bit of room. Then we said that the center of this went away. I think it was at 3, 2, -3. So we're going to say 3, 2, and then -3. Right, so our center is probably like somewhere here. It's going to expand upon the z-axis. Right, so this is probably an approximate picture of what we're going to have. All right, it's probably not a good picture. My suggestion would be to always verify using the GeoGebra app. All right, so hopefully this is a good introduction to be able to identify, classify, and to sketch both these surfaces in 3 dimensions as well as their key characteristics.